In the previous videos, we have created a food source and given the AI the means to find it. What we haven't yet done is create a reason for the AI to seek out the food source in the first place. We also want to be careful that the AI isn't always looking for food, as that isn't very natural either. We will do this by creating a service in the behavior tree that will modify a Blackboard key representing hunger. We will then make the hunger level rise gradually using this service. Finally, we will use a new decorator to control which of our existing sequences will be executed dependent upon this hunger level. We will see how setting things up in this way makes it quick and easy to create complex behaviors simply by reordering the existing nodes within our behavior tree. We'll begin by creating a new service. But before we do that, let's remind ourselves of our goal. Our goal is to create a simple representation of hunger within the AI. We will do this by first creating a new Blackboard key to store this hunger value, and then later manipulate it via a service. We'll begin by opening the existing behavior tree, bt_enemy AI. From here, we'll select the associated Blackboard from the top right-hand corner. We'll add a new key from the Blackboard panel of the float type and name it hunger. With a new key added, we can return to the behavior tree by selecting it from the top right. Now we'll create the new service. Click the New Service button on the toolbar. This will automatically create the new service and open the editor. But before we begin creating this new service, let's tidy up our folder structure a bit more. Minimize the window to return to the content browser. You can see that our new service has been created in the current folder called BT_service_blueprint_base_new. Let's give it a more descriptive name of BTS_hunger. Note that the BTS prefix denotes this as a behavior tree service. Now create a new folder called Services to store this service in. Click and drag the service into the new folder. Now we can return to our service by double-clicking it. Create a new variable from the My Blueprint panel. Name this new variable hunger key. Make the variable type Blackboard key, and ensure that it is set to public so that we'll be able to alter it from the behavior tree later. Now we need to add a tick event to the event graph. This is the event that will fire every time the service ticks within the behavior tree. Right-click on the graph and begin typing event receive tick AI and select it when you can see it. Now we need to get some information from the hunger key we created. Hold down Ctrl and left-click while dragging the hunger key from the variables drop-down into the event graph. Now drag from the hunger key and begin typing get Blackboard value as float and press enter when it becomes visible. Now we have access to whatever the current hunger value is in the Blackboard. Now what we want to do is add a certain float value to this value to represent an increase in hunger during this tick. Drag from the return value of the get Blackboard value as float function and look for float plus float. Now drag out from the second value in the float plus float and promote it to a variable. Name this variable hunger increase rate. Ensure that you make this variable public as well, as we would also like to adjust it from the behavior tree later. With this current setup, the hunger increase rate will be added to the existing hunger value every time the service ticks. However, this means the number would just grow larger and larger, which isn't what we actually want. We'd like to represent hunger as a value between 0 and 1, and we can achieve this by using the clamp function. Drag out from the float plus float function and begin typing clamp float. The clamp function will take the input value and return a value that is between the minimum and maximum defined within the function. By default, the minimum is 0 and the maximum is 1. This is actually what we want. By adding these two float values together, we've created a new value for hunger. What we need to do now is return this value to the Blackboard. Select the hunger key in the event graph and press Ctrl+C to copy it, and then Ctrl+V to paste it. Drag out from the hunger key and begin typing set Blackboard value as float. Now drag from the return value of the clamp function into the value input of the set Blackboard value as float function. Now we can finish up by using the marquee select to select all of the nodes and neaten up the graph. The last thing to do is connect the execution pin from the tick AI event to the set blackboard value as float function. Now we can compile our blueprint by pressing F7 or compile on the toolbar. Once it compiles successfully, we can save and close the blueprint editor window. Now it's time to add our newly created service to the behavior tree. Begin by opening the behavior tree from the content browser. We want our service to be running all the time, and because services only run when that node is being executed, we need to place it on the selector above all the other branches. Right-click on our selector and select Add Service. And now select the new BTS_update hunger service that we just created. Select the new service by left-clicking on it. If we look in the default rollout of the details panel, we can adjust the variables we created within the service. We can adjust the hunger key to point to our hunger blackboard key, and we can adjust the increase rate from 1 to 0.1. Note that also in the details panel, in the service rollout, we can adjust the interval, which is how often the service is ran, and the random deviation. To keep things as predictable as possible for our examples, let's remove the random deviation by setting that to a value of 0. I suggest setting the interval itself to a value of 1. Now our service is up and running, and it will adjust our hunger blackboard key accordingly. What we need next is something within our behavior tree that will alter the order of execution depending on this hunger value. We'll do this by adding another decorator. Right-click on the existing Find Food sequence and select Add Decorator, and then select Blackboard. Left-click on this new decorator to select it. Change the blackboard key in the blackboard rollout to our hunger key. Note that the key value above changes as this is a float value. Change the query so that it says is equal to 1. This decorator will now prevent the Find Food sequence from running until hunger is at the maximum value of 1. To help remind us of the purpose of this decorator, change the node name to isHungerAtMaximum. And with that, we've made the necessary changes to our behavior tree, so we can save and close the behavior tree window. Now let's see what impact our changes have had on the AI behavior by running the game and observing the behavior tree. Before starting the game, reposition the player character so they aren't instantly spotted by the AI, as chasing the player is a higher priority than finding food, and that's not what we want to focus on. Open the behavior tree asset from the content browser before starting the game by hitting play from the toolbar or pressing Alt-P on the keyboard. As soon as the game begins running, press the pause button in the toolbar in the behavior tree window. Ensure that our AI character is selected from the drop-down in the toolbar. Let's maximize the behavior tree window and review what's happening. Moving to the bottom right in the Blackboard panel, we can see our hunger Blackboard key is currently set to a value of 0.1. This means we considered the AI not hungry enough to look for food. Looking at the behavior tree, we can see that the random wander sequence is the one that is currently being executed. If we press the Back Into button in the top toolbar, we can see exactly how we ended up in this situation. First, the selector above tried the chase player sequence, but the decorator prevented it because no target actor is set. Target actor is something we set via the perception system, and as the AI has not seen the player, this has not been set. Next, the selector will try the Find Food sequence, but again, this will also be blocked by the decorator. This decorator will only allow the Find Food sequence to be executed if the hunger Blackboard key is equal to a value of 1. As that is not currently the case, this sequence will not be allowed to execute. This leaves the final sequence, the lowest priority sequence, the random wander. The random wander sequence has no decorators associated with it and thus nothing to prevent the execution. If we hit resume in the toolbar and then move our focus to the Blackboard panel, we will be able to see the hunger Blackboard key increase each time that the BTS_hunger service ticks. Once the Find Food sequence is triggered, press pause so we can review how this occurred. Press the Back Into button on the toolbar until the action highlighted is the wait task completing. Here we can see the wait task of the random wander has been completed, and so this sequence is also considered complete. The sequence then moves back to the selector. This means that the sequence will report that it has succeeded to the selector. Once again, the selector will have to review all the sequences below it. Press forward into to see the next stage. Once again, the selector starts with the highest priority task. As a reminder, priorities in behavior trees go from left to right, so the highest priority sequence is the chase player sequence. However, this is still blocked by the decorator. There is currently no target actor value set for the Blackboard key, and so this sequence will be blocked by the decorator. The selector will then try the next priority sequence, which is the find food sequence, and this time the decorator will allow execution because the current hunger value is equal to 1. Press forward into it again to see the next step. First, our EQS query is ran and a food source is located successfully. This means the sequence continues to the move to. The move to task uses the target food source Blackboard key set by the previous query as a target. When the AI reaches this location, the move to returns success, and so the sequence continues. The next task in this sequence is a simple wait. We can now hit resume to see what happens next. You'll now notice our first problem. The hunger Blackboard key always remains at 1 once it reaches this level. This means that once it reaches a value of 1, the find food sequence will always be allowed to execute by the decorator. The next step will be to implement some simple logic that will reset this hunger Blackboard key. What we need to do next then is create a new task. This new task should reset the hunger Blackboard key to a value of 0. We will deliberately make this new task generic, that is to say, something we can use anytime we want to manipulate a float Blackboard key. In this instance, we'll change the value to 0, but in theory, we could change it to anything we wanted. Begin by creating a new task by selecting the New Task button from the toolbar. Select BT_task_blueprint base as the base for our new task. As before, this will create the new task and open it automatically in the editor, but I prefer to sort out our folder structure before working here. Minimize the Blueprint editor to return to the content browser. Rename this task BTT_set_key_float. With that done, drag it into the tasks folder. Now we can open the tasks folder and double-click the new task to return to the editor. We'll begin by adding the Blackboard key variables we need. In the variables section of the My Blueprint panel, press the plus icon to create the first variable. Call this new variable float key, and in the details panel on the right-hand side, change the variable type to Blackboard key selector. Return to the My Blueprint panel and ensure that the float key is made public, as we will need to manipulate it from the behavior tree. Repeat the process to add another variable. Call this new variable float value. In the details panel, change the variable type to float. And once again, ensure that this variable is public. With our variables added, quickly compile the blueprint by pressing F7 on the keyboard or hitting the compile button in the toolbar. Now we need to add a similar setup of events that we've used in previous tasks. Begin by right-clicking in the event graph and begin typing event receive execute AI. Now we will use our variables to set the correct Blackboard key to the desired value. Hold down the Control button on the keyboard while left-clicking the float key in the My Blueprint panel and dragging it into the main window. Drag out from the float key pin and locate Set Blackboard Value as Float. Now we just need to connect our float value variable to the value input of the Set Blackboard Value as Float function. Hold down Control on the keyboard and left-click and drag the float value into the window. Connect the float value to the value input of the Set Blackboard Value as Float function. Now we can connect the execution pin from the event to the function. Now we need to make sure that we return success from this task, otherwise the behavior tree will get stuck waiting for a return value. Right-click on the graph and locate the Finish Execute function. Be sure to check the success ball within the function. Then connect the execution pin from the Set Blackboard Value as Float function into the Finish Execute. We can now save and compile this blueprint. Now let's return to the behavior tree and make use of the new task we've created. Reposition the random wander sequence to give us a little bit more space on the left-hand side. We're going to place this task after the wait task in the find food sequence. The assumption is that while the AI is running the find food sequence, assuming they are able to find the food, move towards the food, and be able to wait for 1 second uninterrupted, then we can consider them to have eaten the food source. So after the wait task, we will add our new task to reset the hunger Blackboard value. Drag out from the sequence and find our new task, btt underscore set key float. Move over to the details panel and set the float key value to hunger and the float value to 0. That's the only change we need to make to the behavior tree, so hit Ctrl S or hit the save icon to save the changes to the behavior tree. Now we can run the game again and see what difference this change makes. Once again, we can pause after the hunger blackboard value has been reset and use the Back Into button to step backwards through the behavior tree tasks. If we move back to this stage, where the wait task has just returned success, we can see that our btt underscore set key float is just about to be run. Moving over to the blackboard panel on the right hand side, we can see the hunger value is currently set to 1. Now if we press forward into to step forward, we can see what happens next. The btt underscore set key float task has completed. It has returned success to the sequence. We can see that it's been successful because the hunger value in the blackboard is now set to 0. Because the find food sequence is now complete, we return to the selector. If we press forward into again, we can see what happens next. The chase player sequence is still blocked by the decorator. This is because target actor still has no value set. We can see that the find food sequence is also blocked by the decorator, as resetting the hunger blackboard value to 0 means that the hunger value is no longer equal to 1, which is the condition of this decorator. That means that the AI will once again return to the random wander sequence. And if we hit resume, we can see that the hunger value continues to increase. When it reaches the value of 1, it will return to the find food sequence. Hopefully now you're starting to realize the power of behavior trees. This very simple setup, with the use of a handful of decorators and blackboard keys, is already creating a relatively complex behavior. We have a series of sequences that are organized in terms of priority, and an AI that will pick these based on the current conditions. In this video, we created a new hunger blackboard key and manipulated it directly from the behavior tree using a service. We learned that a service is a self-contained blueprint script that will run at a fixed interval for as long as the branch it is part of is executed. The service we created increases the value of the hunger blackboard key up to a maximum value of 1, representing maximum hunger. We then use this hunger blackboard key with a blackboard decorator to control execution flow. The decorator will stop execution of the branch that makes our AI search for food until the hunger value is sufficiently high. This configuration demonstrates the power of behavior trees when used in conjunction with decorators. With just a few small changes, we can completely change the behavior of our AI.